welcome back. If you've forgotten who I am, I'm Ashwin Nayak from University of Waterloo, and today I'll switch topics to quantum algorithms. In fact, this is such a vast topic that I decided to not talk about quantum algorithms, but one quantum algorithm which should give you a flavor of what these things look like. It would be a pity if you came to an introduction, introductory school on quantum computation and you didn't see Shor's factoring algorithm. So I thought I would present that to you as a representative of the power of quantum computation, and also as a representative of what we think of as an efficient algorithm. It so happens that there is a view of Shor's algorithm that is quite simple. In fact, it can be related to things that you are already familiar with in physics. In particular, it's related to this notion of phase estimation. My knowledge of physics is not good enough, so I might make mistakes in what I'm going to say, but I think it's my understanding that this is a very rudimentary understanding of light, but light has this property that definitely when it's reflected there is a phase flip in it. Also, when it's transmitted through certain materials, it undergoes a phase shift. And there is a standard experiment in optics that helps us determine what this phase shift is. So let's look at this experimental setup. Imagine there is this crystal here which introduces this phase shift, which is what we want to measure. What we do is we shine a beam of light onto a half silvered mirror which splits it. So this is a beam splitter. It splits it into two parts, and one of these two parts is what we send through this crystal. So we reflect it again. It passes through this crystal, which introduces a phase shift of e to the I phi. And what we do next is basically recombine it with the light that's coming in the other path and observe what the intensity of light is here. The intensity of light here contains all the information you need to know about the phase that was introduced. There is a quantum information way of viewing this entire experiment. In fact, it is a simple quantum algorithm. I can draw it in the form of a circuit, and this is how it looks. Basically, we have one qubit that indicates what path the beam of light will take. We split the beam into two parts, and this is accomplished using this Hadamard transformation. Now this single qubit, which contains information about whether light was reflected or was transmitted, goes into a superposition of the two possibilities. Now here's a state that represents the rest of the properties of that beam of light. At this point, the top beam of light encounters a phase shift, whereas the bottom one doesn't, and that's denoted by a controlled phase shift operation, meaning whenever the top qubit is 0, nothing happens to the beam of light, but when it's 1, you get a phase shift of e to the I phi. Finally, you recombine the two beams using the same operation, and you make a measurement. So this part is measured, and this part is simply left unchanged, unobserved. Now this gate out here is something that you've seen in Barry's talk yesterday. Oh, in the diagram on the left? Okay, so this reflects my poor understanding of physics. Yes, there is a difference in the length of paths. You can arrange it so that, the extra length in path is precisely so that, there is no other phase shift apart from e to the I phi, right? You can do that. Okay. So let's trace the state of the joint state of this quantum system out here through this circuit to see what happens at the very end. What will you observe out here? So I can write this state as 0 C. The Hadamard transformation basically converts the 0 into an equal superposition of 0 and 1. Now, this is basically the Hadamard on the first qubit, tensor with identity on the rest of the state. The next is this controlled phase shift. So I'll write this as controlled e to the I phi, which means if the first qubit is 0, nothing happens to the state, whereas if this is 1, there will be a phase kickback of e to the I phi. So the state becomes 0 C plus e to the I phi 1 C. Here. If you notice, I can factor this state out as 0 plus e to the I phi 1 followed by psi, right? So it's still a tensor product state in spite of the fact that there was what looked like an entangling operation between the two paths. Now we have a final Hadamard transformation, and when you run through the algebra, what you see is that the first qubit ends up in state which is 1 plus e to the I phi over 2, 0 plus 1 minus e to the I phi over 2, 1. And of course this is in tensor product with the rest of the state. So at this point we make a measurement here of the top qubit, and what we get is either 0 or 1, one of the two possibilities. You get 0 with probability which is the amplitude squared, 1 plus e to the I phi over 2 modulo squared. And if you simplify this, do some algebra, what you get is cosine squared phi over 2. Okay, which means that you get 1 with probability equal to sine squared phi over 2. Now, this is directly related to the phase that we were interested in, phi, right? If you repeat this process, if you repeat this phase estimation circuit several times, you will be able to estimate sine squared phi over 2 by simply looking at the number of times a 1 occurred in your measurement outcomes, right? And the question you might ask is, well, how many repetitions do we need? Because, of course, we want this entire process not to take forever. And fact is that to estimate phi to within accuracy, which is delta, we need something like order 1 over delta repetitions. Okay, and this follows basically from some elementary probability theory and also elementary calculus. Okay, now if you really wanted to be very precise in how what your estimate of phi looks like, then you would want delta to be of the order of phi or little o of phi, right? And this is what we would need in our application, the application that I'm going to show you in 10 minutes. We'll need delta to be little o of phi, which means that we'll need something like omega of 1 over phi repetitions. And it'll turn out to be too expensive, too prohibitive. Okay, so the question is, can we do this phase estimation procedure in a more efficient fashion? Now, by more efficient, what we would like to aim for is the number of repetitions be not 1 over phi, but 1 over log of phi, meaning 1 over the number of bits of precision that we need in writing phi out. And turns out you can do this provided you have a way of introducing not just the phase shift e to the I phi, but various multiples of this. So what multiples of e to the I phi do we need? We need phase shifts that are basically phi, twice phi, 4 times phi, 8 times phi. So all power of 2 multiples of phi. Okay, so let me, for convenience, introduce some notation, which is that this operation here, this phase shift operation, let me call it U. We'd like to be able to apply phase shifts which are U squared, U to the fourth, U to the 2 to the I, all the way up to U to the 2 to the M. Okay? So whenever you apply U to the fourth, for example, you introduce, well, this phase shift e to the I phi 4 times, which is what gives you a phase of 4 times phi out here. Now, it's not at all obvious that you can do that without basically repeating U as many times as we need. But again, we turn out to be lucky, and in this application we'll see, we'll be able to do this efficiently. Okay, now I've talked about this application a few times without even stating what it is. So let's go and see what this computational problem is. To see what this is, I'll have to make a few definitions from number theory. So we'll start with n being some positive integer, and as I've already said, I'll be talking about the Shor algorithm. So this n is what you should think of as the number that is being factored. Okay? But that's not the original problem. Well, that's not the problem that I'll talk about first. We'll come to integer factorization after we look at a related problem. Okay, and the related problem is the one that we'll solve using a quantum algorithm. And later on, we'll see how the result to this related problem can be used to factorize integers. That part is entirely classical, meaning we don't need qubits or unitary operations or measurements to implement that part. We need basically, the computers that we have today. So let's get back to this related computational problem. N is some positive integer. We look at all the integers x that are co-prime with n. We look at the set z star sub n of integers x between 1 and strictly less than n, such that the GCD of x and n equals 1. Now this set forms a group under multiplication of integers. So this is an algebraic group. So one thing that this implies is that if you take any number in this set and take its successive powers, at some point you will circle back to 1. So for any x in this set, in this group, there is some integer, let's call it s, such that x raised to power s will be equal to 1. Well, I guess I didn't mention this. This is not just multiplication, it's multiplication modulo n, meaning whenever you multiply and get a number that's bigger than n, you simply take its remainder, right? So this is under multiplication modulo n. Otherwise, of course, when you multiply, well, take powers of numbers in this set, you're going to get numbers that are in general larger than 1. So clearly, you can't get, as you take powers of x for, x that is not 1 to begin with, you can't get distinct powers all the time, simply because there are a finite number of remainders modulo n, and you are bound to hit one of them ultimately, right? Fact is that you hit 1, you definitely hit 1. The smallest integer s for which this happens is called the order of x. And it's denoted by ord sub n of x. Okay, let's look at an example. I think it'll help to see what we are talking about. Let's take n to be 21, and let's look at z star 21. This is the set of all integers between 1 and 20 which are co-prime with 21. So the numbers are 1, 2, not 3, 4, 5, not 6, not 7, 8, not 9, 10, 11, not 12, 13, not 14, not 15, 16, 17, not 18, 19, and 20. Right? Now, let's take a number for which I've calculated powers, just so you see that I'm not joking about all the numbers being having an order, a well-defined order. Consider powers of the number 10, which belongs to this set. So in the first row, I'll write down the power the exponent, and in the lower row I'll write down the power. So this is 10. 10 squared is 100. When you reduce it modulo 21, you get 16. Now, I haven't done these computations myself. I picked it out from a colleague's slides, so I hope they are correct. I think we can all verify back at home whether they are or not, but here are these numbers. And when you take 10 power 6, you see that you get back to 1. And after that, 10 power 7 modulo 21 will again repeat the same sequence of integers. So 10 power 7 will give you 10, and 8 will give you 16, and so on. So now I'm in a position to define what the order finding problem is. For this problem, there are two inputs. One is an integer n, and the second one is an integer a, which is in z star n. So this integer is between 1 and n minus 1 and has no common divisors with n. The output that we want is the order of a with respect to n. Now, if I asked you to find the order, the straightforward way of doing it would be basically what we did out here for 10. We would take 10, multiply 10 with itself, take the remainder modulo n, and repeat that until we get remainder 1. The first time we get remainder 1 is when we have hit the order. The number of operations that we need for that straightforward algorithm turns out to be, well, precisely the number, well, that we are looking for, the order. Right? So the complexity is something like order, well, this number that we are looking for, and in the worst case, well, this is at most the size of this set or this group z star n, and it's definitely less than n. It's actually what's given by the Euler-Toshan function, but we won't really bother about that. Let's just give a loose bound, which is order n. And this is the number of multiplications, modular multiplications that we need to do. Now, multiplications are actually cheap operations, computationally speaking. Meaning, if I give you two k-bit numbers, then to multiply the two k-bit numbers, the number of, even if you do it by the method that you learned in, in primary school, then you would take k-squared operations to do it if it's represented in binary. There are faster ways of doing it. In fact, you can do it in k times log log k bit operations, but we won't really bother about that because the first procedure itself, the one that we learned in primary school, is efficient. So today we'll not worry about elegance and the best possible algorithm that we can construct, but simply one that is efficient. So if you look at the numbers involved in this problem, they are n and a. The number of bits that it takes to represent these two numbers is log of n. So the input size is basically 2 times log base 2 of n. And your complexity is order n, which is exponential in this input size. Now you might wonder why this is important. Well, it's important because if you take an n, which is, let's say, 1,000-bit number, then it'll take you forever. In fact, it'll take you beyond your lifetime to follow this procedure, this straightforward classical procedure, to compute the order of a number. And this is, of course, not the best classical algorithm to do this, but even the best classical algorithm that is known today is not polynomial in the input size. So it's not known to be solvable in time that is polylogarithmic in n. Nonetheless, there is a quantum algorithm that we'll see in a moment that can help us find this order in a number of arithmetic operations that is polynomial in log of n. And it takes us back to this algorithm that I described at the very beginning, which is this phase estimation algorithm. I should mention that this phase estimation algorithm is one that was discovered by Alexei Kitaev when he heard of Shor's algorithm, and he was back in Russia, I think at the Steklov Institute, and he hadn't read the paper, but he had this insight into both computation and into quantum physics that allowed him to rediscover this algorithm independently of Shor's. I should also mention that the presentation that I'll make is his original version of the algorithm, which has later on been refined so that it's more efficient, but I'm presenting the original one simply because it's more elementary. It basically uses what I showed you before, phase estimation, and some elementary linear algebra. Okay, so let's see how you find the order of a number modulo n using phase estimation. Well, to do this, I have to define for you two things. One is, what is the state into which a phase will be introduced, and what is the unitary that is going to introduce the phase? The unitary is easier to describe, so let me do that first. So consider a unitary U. This will be defined on a state which comes from an R-dimensional complex Hilbert space. And what is this R? This R is actually the unknown order of A with respect to N. Now, turns out that you can implement this U without knowing R. So it's not a problem that we are using operations that depend on R implicitly. I'm going to give this a subscript of A because this unitary will depend on the input A that we have. And how is this unitary defined? It's actually given by a classical definition, meaning whenever you are in state X, where X is basically a representation of the number, of a number in between 1 and n, then this unitary multiplies X with A. So the result is A times X modulo n. And fact is that this is an invertible operation. Because A is co-prime with n, there is a multiplicative inverse of A in Z star n. And this is something also a consequence of some elementary number theory, which I just recommend you take at face value if you don't know it already. Okay, so that defines our unitary for us. And we'd like to see the state into which this will kick in a phase. So consider this special state. And you'll see that the state that I'll write down, which I write down as C sub 1, also depends on R, which is something we do not know. And this will be a problem for us, but we'll see later on how you can overcome this problem. So let's look at the state, which is an equal superposition of j going from 0 to r minus 1 of omega to the j a to the j mod n. If you look at all the powers of A between 1 and its order, so the first R minus 1 powers, they are all distinct numbers, so that this is an equal superposition of these powers of A. Okay, let's see what happens when you apply U sub A to C1. Oh, maybe I should also tell you what omega is. Let's see. So omega is a phase which is given by J and R. So it's 2 pi I being the complex square root of -1 times J divided by R. Actually, there's a negative sign here for convenience. Okay, so let's see what U sub A applied to C1 is. This is 1 over square root R, summation over J, omega to the J. You multiply the number here by A, you simply get the next higher power of A. a to the j plus 1 modulo n. I can rewrite this as, well, omega to the minus 1. So I can multiply the phase by omega and divide it by omega to get this expression here. So I have omega to the j plus 1 and a to the j plus 1 mod n. If you see here, what we have here is a sequence of powers of a which I've shifted by 1. Earlier I had powers of a going from 0 up to r minus 1, but now I have them from 1 to r instead. And you've seen before that the powers of a actually cycle, so that I have the same powers of a as I had in my original superposition here. So in fact, this state is nothing but omega to the minus 1 times C1. So applying U sub A to C1 introduces a phase of omega to the minus 1. And just as a reminder, this is simply the exponential of 2 pi I divided by R. Sorry, did I write J here? This J is extraneous. The jth power of A, sorry, omega is already written here explicitly. I wanted this to be e to the minus 2 pi I divided by R. Okay. Now why is this interesting? It's interesting because this phase contains exactly what we wanted to compute, R, which is the order of A with respect to n. So if we implement phase estimation on the state C1 with respect to this operation, which is multiplication by A, which is an efficient operation, then we can compute R by using our phase estimation algorithm. Right? So that's basically the idea behind computing the order. Now there are two details that we need to figure out in order to complete the picture, which is, one, to efficiently be able to estimate the phase, we need not only to be able to implement U sub A, but power of 2 u raised to powers of 2. And furthermore, we need to be able to construct the state C1. So let's see how you tackle these two problems. So we need one, an efficient computation of u sub a raised to 2 to the I, and 2, a construction of C1. So let's look at the first one here. As I said, one way to do it is simply to take u, apply it 2 to the I times, but that is going to be too expensive. So instead, what we do is something slightly cleverer, and for that we need to go back and see what this definition of u sub a is. U sub a applied 2 to the I times to a number x actually gives us a multiplied 2 to the I times to x, right? So this is simply a raised to 2 to the I times x modulo n. Now we need to be able to figure out an efficient way to multiply a to the 2 to the I with x. Here's how you do it. You have a with you, that's the input. So this is, whatever I'm describing is a classical algorithm, and there's a straightforward way of doing it on a quantum computer. You take a and you square it. You get a squared. Now instead of multiplying a to it to get a cubed, a to the 4th, a to the 5th, and so on, you simply square a squared again. You get a squared squared, which is a to the 4th. You square that once more, you get a to the 4th squared, and that's a to the 8th, which is a to the 2 cubed. You square it once more, and as many times more as you need. In fact, if you square it I times, you get a raised to 2 raised to I. So instead of having to do this multiplication 2 to the I times, you're able to do it in simply I times. So that's an exponential decrease in the number of multiplications that you need to make. Remember, this is all modulo n. Modulo n simply means that whenever you get a result that's more than n, bigger than or equal to n, you divide by n and just stay with the remainder. So now you have a raised to 2 raised to I mod n, and you simply multiply x with this. There is a subtlety in this description, which is normally when you compute on a classical computer, you're left with all your intermediate calculations. So in particular, you might have a squared, a to the 4th, and so on left over, or at the very least, you'll have the final number a to the 2 to the I left over with you. And in quantum computation, it's quite important for your computation to be clean, meaning you don't want your rough work, so to say, be left behind in memory, because that obstructs interference. Just the way your phase estimation algorithm, the procedure, would have failed had you also kept around this information as to whether your beam of light went from the path above or from the path below. So it's important to remember that any classical computation that you do like this can be reversed so that all the intermediate steps are cleaned up. So I'm not going to write that down, but it's something that one should keep in mind. Okay, so this leaves us with an efficient implementation of u sub a raised to 2 to the I, which is what we wanted to accomplish. Okay, that leaves us with the second step, the second issue that we have to face. We'd like to somehow construct C sub 1. Actually, we are going to cheat. We are not going to construct C sub 1. Instead, we're going to work with a state that's completely different. And that state will involve not just this C sub 1, but other related states that look similar to C sub 1. We'll work with states C sub k, where these are uniform superpositions, and they look quite similar to C sub 1. They are uniform superpositions of j going from 0 to r minus 1. And here you have omega not to power j alone, but j times k. And we'll work with these states for each k going from 0 up to r minus 1. Now, at the face of it, the situation looks worse than before. We didn't know how to construct C1, and these states are actually similar. So how are we going to work with these states? Turns out that if you take a uniform combination of all these states that we have here so far, then the resulting state is something that is simple to construct. So you consider instead this uniform superposition over all the pk's. Take k going from 0 to r minus 1 of ck. Let's look at what this is. This is 1 over square root r, summation k, summation j, and we pick up another 1 over square root r from here, so that this is really an r. Here you have omega to the jk, a to the j mod n. Both of these ranging from 0 to r minus 1. Okay, let's do some algebra. I'm going to switch the order of summation, and you'll see in a moment why. So here you have j and the summation over k, omega to the j raised to k, a to the j mod n. Now if you look at the amplitude of a to the j, it's a sum of powers of omega to the j. Each omega to the j is an rth root of unity. And you know that when you sum up powers of any root of unity, rth root of unity going from power 0 to power r minus 1, you're going to get 0 if it's a non-trivial root of unity. And the trivial root of unity is, of course, 1. And for that, you would simply get r in the summation, right? So this simplifies as follows. Summation over k going from 0 to r minus 1, omega to the j to the k equals 0 if j is non-zero, and then it equals r if j equals 0. So that whole summation simplifies to a single state where j equals 0. A to the 0 is simply 1. So this uniform superposition, 1 over square root r ck, equals simply the state where you have the number 1 written in your memory. Okay? And that is something which is easy to construct. Right? You can simply write that down. Now you might ask, we wanted to work with a state C1 which gave us information about phase which contained R, but now we are working with a superposition of CKs. Question is, what is the phase that is introduced because of CK? Is it the same as omega? If it is, we are in good shape. If it's not, we need to worry about what information that gives us. And further, we need to worry about what happens when we work with a superposition of these CKs instead of simply one of them. Again, luck is in our favor, and both of these problems turn out to be non-issues. So let's look at the first one. Let's look at the phase kickback on CK. When you multiply CK by UA, and you can do this on your own, what you see is you get a kickback of omega to the k. So the eigenvalue corresponding to C sub k is omega to the k, which basically is the exponential of 2 pi I k divided by r. Whereas C1 gave you 1 over r as essentially the phase information that our estimation procedure gives us, here you would get k over r. Right? And well, this is not too much worse than getting 1 over r, because if k and r are co-prime, then the fraction, when you write this number, your estimate as a fraction, you can read off k and r from the numerator and the denominator. Of course, if k is 2 and r is 4, then k over r will be 1 over 2, and you won't get the correct order from this. But again, most of the k's between 0 and r minus 1 are such that k and r are co-prime. So r, in fact, r some constant times r divided by log r of the k's in the range one up to r minus 1 are co-prime with r. So most of the k's will work and will give us the order r using the phase estimation procedure. As I said, we are not working with a particular psi sub k. Instead, we are working with a uniform superposition of these psi sub k's. So we won't get a particular psi sub k or a particular k here, the state 1, the procedure estimates or outputs k over r in the component containing C sub k. Observing the output will give you k over r for a random k. And with probability which is 1 over log r, this gives us the correct r. Now why is this good enough? It's good enough because we can repeat this entire procedure log r times and get the correct order. Okay, and well, you might ask me finally, how do you know that you have the correct r? You can simply check. You can raise a to the power r and you can check that it equals 1. You see, whenever you fail, whenever you get a k that is not co-prime with r, you'll get a number that is smaller than the order, and raising a to that power will not give you 1. Okay. So this completes the description of the order finding algorithm. Maybe I should pause. I haven't paused at all in this entire description. Are there any questions so far? Yeah?
Very elementary, you already explained it, but so far
Right.
And then if you pull out this, as you said, 2 pi A by the coefficient of psi k.
Right.
Do that, you have to have some a priori knowledge of psi k, because psi k was defined implicitly with R.
Right.
So that's what I'm confused about.
The a priori knowledge that we work with is that the state 1 is this uniform superposition of the psi k's. Now, we need only construct the state 1.
Yes.
And nature will take care of the fact that it's this uniform superposition.
Right.
So that's where we...
What about the phase estimation? How do you pull out the coefficient of psi k?
Okay, so look at what happens. Let me not write it this way. Let me write it as, we know the following. That the phase estimation, let me write it as PE. So PE is a unitary circuit, I mean it's a quantum circuit, which depends on this unitary U sub A, which when applied to psi k gives us, well, it leaves psi k here unchanged, but it writes down in some extra registers the value k and r. Okay, let's imagine this is how it works, right? Now, we know that quantum mechanics is linear. So if we work with a superposition of psi k's, then this procedure will act linearly on that superposition. So if now you apply this phase estimation procedure to 1, then it's going to act linearly on the superposition. Right? And the result is going to be exactly a superposition of these states. So you're going to get a sum over k, 1 over square root r, ck, followed by k comma r. Now when you measure this register, you're going to get k and r for a random k. Okay? And then you follow the rest of this sequence of operations. Other questions? Okay, I have 5 minutes, and in those 5 minutes I'd like to explain why order finding is relevant for factorization. And this is, well, elementary number theory, but it wasn't elementary to me, certainly when I first saw it. So I don't expect you to know it or fully understand it immediately, but it's good to know this connection. So I should remind you that the quantum algorithm, the quantum part of the algorithm, basically finishes with order finding. Once you have this quantum algorithm for order finding, the rest of it is all classical. Okay, so let me just state a few facts about factoring integers. So let n be this integer that we want to factor. The first fact is that it suffices to find one factor, one non-trivial factor of n. Meaning it suffices to construct an algorithm if you find, let's say, a factor s, and of course the remaining factor is n over s, then you can run the same algorithm recursively on s and n over s until you find all the prime factors. Okay, so that's a simple part, a simple case of factorization or property of factorization. The second property that is actually not well known, and I didn't know it until I did until I did a graduate course in algorithms. But this is something that you could do if if you've learned what's known as binary search, which you do in in your undergrad education in computer science, if you happen to do it. And turns out that if n is of the form p to the k for some prime p and an integer k bigger than or equal to 1, then we can do this classically efficiently. Okay, so if you look at these two properties of factorization together, then it leaves you basically with finding a non-trivial factor of n when you know that there are at least two distinct prime factors. Okay, and this is where order finding comes in. When n has two distinct prime factors, we have the following property satisfied by numbers that lie between 1 and n. A constant fraction of numbers a which are in z star n satisfy the following conditions. One, that the order with respect to n of a, let's call it r, is even. And two, a to the r over 2 plus 1 shares a non-trivial factor with n. Okay? So if you've ruled out the possibility that n is a prime power, then all you need to do is you pick a random a in z star n, you find its order using our quantum algorithm, you compute a to the r by 2 plus 1, take the GCD with n, and that will be with high probability of a non-trivial factor of n. So I won't prove this fact from number theory for you. I'll just write down the final algorithm. Step 1 is you check if n is of the form p to the k, that's case 2. If yes, you're done. And otherwise, we are in case 3. We'd like to find one non-trivial factor of n. You pick a from z star n uniformly at random. Okay, how do you do this? Let's just write it out in full. So pick a number a between n minus 1 and 1 uniformly at random. Check if it's co-prime with n. If not, you have a non-trivial factor of n, so you're done. And if it is co-prime, then we kick in this order finding algorithm, because we have a random number from z star n. Well, let's write it as a is in z star n. We compute the order of a with respect to n. Using our quantum algorithm, right? And now if r is even, compute the GCD of a to the r over 2 plus 1 and n. If we are lucky, then it shares, well, it gives us this non-trivial factor of n with constant probability. We get a non-trivial factor. Right? And if even this fails, which happens with a small constant probability, you go back all the way to step number 2, to A. And you repeat. And you need only repeat this a constant number of times because your success probability is a constant. right? So that's the algorithm in its entirety. And let me stop here for questions. All right. I'd like to think I did such a good job that it's perfectly clear to all of you. Thank you.